everyone, welcome. What I'm going to do in this video is talk about resonance of closed pipes. So what I'll do is first I'll draw all the resonances, or at least the first couple resonances in the closed pipe, talk about the nodes and antinodes and the wave patterns that are formed in there, and then show you the equation derived for solving problems with closed pipe systems. So here we go. What I'm going to do is we're going to draw our harmonics in closed pipes. So let me go ahead and lock this in. And because I can use nice straight lines, I think I will. Let's change that to black. So closed pipes will look kind of like what you expect. One end will be closed like this, and then one end will be open. So let's see if I could actually, let's go back. Okay, that'll be good enough. Actually, I guess I should draw the next couple. As you might imagine, these won't be super perfect in terms of the drawings, but you get the idea here. I would like to draw at least the first four, so give me a minute to draw them. The pipes, that is. So you can see the pattern that forms. Okay. They're not perfectly straight, but that's okay. Alright, so the rules with closed pipes is that when you, just like before with open pipes, you're going to have an antinode here. That's because the air is going to be allowed to move the most at the end of the pipe when we drop the wavefront in it. But at this point, the air gets trapped, so it causes the air to kind of compress there and not move, which means we always form a node right here. Okay, so there's always, by rule, will have to be a node at the end of the pipe. So that's true all the way down regardless of our harmonic number. And then vice versa. The antinode here must always be at the end of the pipe. I don't know why I wrote that one there. Here we go. Like this. Okay, so when we fit a standing wave, remember, I'll draw our reference wave. So remember, by definition, this is just a line, a full wave cycle is when we go up and back down, right? So that's one full wave. And notice, although this is not entirely true, but one way we can think about it, every time this happens, that's a node. And every time this happens, that's an antinode. Just like that. So coming to here, the fundamental frequency, remember, is the lowest frequency that can fit in the pipe. So notice that the lowest frequency is between a node and an antinode. So if you notice, that's basically this part of our wave, the node and the antinode right there. So that's the lowest and basically smallest part of the wave that we can fit. So I'm going to draw this out. And this is really big. So notice that essentially I'm going to draw this line from here to here. But since it's so wide, it's going to be like really weird and stretched out. Sorry, it's not the best of drawings with this pen, but there you go. So I hope you notice that I drew this, basically, this part right here. But, like I said, it's really stretched out, so you get this effect right here. And notice that from here to here, that's a quarter of the wave. From here to here, because that would be a quarter, this would be half, quarter, half. So fun fact, between a node and an antinode, it's a 1/4 wave. And notice that between a node and a node, that's a half of a wave. Just some facts for you right there. Okay, so anyway, so that's a quarter of the wave. So if we did our theory, which we said before, is that how much of the wave fits in this pipe. So remember, this pipe is length L, this whole thing. I would say, actually, I like this, but I'm going to move it because it's in my way. I'm just going to rewrite it really quickly up here, that from node to antinode is always a quarter of a wave, and from node to node, that's a half a wave. Okay, so in this pipe is a quarter of the wave. And then if I rearrange this, we get, move out of my way, okay, we get 4L is equal to wavelength, just like that. And you know what, just to be consistent, I'm just going to put the 1 underneath here, because notice that basically I flipped this over. So this is kind of silly, I know. This is 4 over 1, you're like, oh, that's 4L. You're right, but there's a reason why I'm going to do this. Okay, let's draw the next wave. So the next wave, I'll have to put an so we have a node and an antinode. So notice that from here to here, we have this. But to fit the next wave, it won't be a node to node because the end of the pipe has to be an antinode. So I have to go node, antinode, node, antinode. So about here. So I'm going to put the node to try to break this up as best as I can. So node, antinode, node, so about here-ish. And in between any two nodes is an antinode. So basically I'm going to draw from here, I'm going to go up and then down. So let's draw that. So I'm going to go up. Sorry, my drawings are so bad, I'm so sorry. Up and then down like this. And again, it's really squished. So you'll see a loop right here. And then just like that. So I hope you notice how much of the wave we have in here. So actually using this idea, remember from node to node is half a wave. And then from node to antinode is a quarter. Or if you notice, I have 3/4 of a wave. So 1/4, 2/4, 3/4. So writing that out, I have chopped in this pipe, I have 3/4 of a wave. So not the whole wave, but most of it. Notice that we ended here in this case. So if I rearrange this, this becomes 4 over 3 L equals wavelength. Just like that. Alright, so let's continue. So if I wanted to make the next wave that fits in here, if I continue this, so remember the mark of the full wave is here, but I'm just going to keep drawing a wave to help us visualize what's going on. So I have to add another node, but remember I must end on an antinode because the pipe is open. So I'm going to go ahead and do that. So I'm going to try my best here. Okay. So if you notice, this is our nodes, and in between any node is antinodes. So notice what we're drawing here. Node, antinode, node, antinode, node, and we end here for the next one. So I'm going to draw up, down, and part of the way back up. I'll do that as best as I can. So up, and then down, and then up. And then, of course, the dotted line, remember, is a reflective wave, which just mirrors the incident wave like that. Okay, so in this wave, notice that we go up, down, and back, so that's 1, and a quarter. So we have 1 full wave plus a quarter of the wave. So we have 1 1/4. But I'm going to write that in a weird way. I'm going to do 5/4, because you notice that basically is 1/4 is 4/4. I'm sorry, 1 whole one is 4/4 plus 1 extra one would be 5. And then we get 4L/5 like this. Excuse me. Alright, I'm going to do one more. I'm going to go extra fast. Notice I'm going to add a node. 1, 2, 3 nodes. And then the antinodes are in between. So it will look like this. I'm going to go up for an antinode, down. So that's 1 full wave, up, and part of the way down. Almost 2, but not quite. And there we go. So I hope you notice, remember that one of these between 2 nodes is half a wave. So 1/2 plus 1/2 is 1. This is 1 1/2. And then from a node to antinode is a quarter. So I have 1/2 plus 1/4 is just 3/4. So 1 wave is right here. And this is 3/4. So trapped in here is 1 3/4 wave. So remember I could write 1/4, or 1 wave is 4/4. So 4/4 plus 3/4 gives me 7/4. Oops. Which then means that I have 4L/7 in here. So I do this out to show you one really interesting fact about closed pipes. If you recall when we did open and pipes and strings, that there's a pattern, right? Notice that the 4 is always there. And the thing that changes is going to be this right here. Notice we have 1, 3, 5, and 7, like this. So with that said, notice that these are odd numbers. We can only have odd numbers for our harmonic systems of closed pipes. So n equals 1 here, n equals 3, n equals 4, and n equals, oh, I'm sorry, wow, big error right there. I was counting and not thinking. N equals 5, there we go, and n equals 7. So we can only have odd harmonics. Only. Now the reason why it's only is because of this condition here that we must satisfy, since we have to always have an antinode here and a node here. We're always selecting quarters of a wave. Whereas before, notice that when we had a string, we were selecting halves, right? And with open pipes, it was the same thing, but just a weirder way, but we were always selecting halves, which allowed us to break it apart evenly. But this we can only do in odds. So, and then notice that pattern here, right? 1, 3, 5, 7. So let me derive out the equations that we get from this. Screenshot. So for closed pipes only, L is equal to n wavelength over 4. Big difference, where n is odd. It's restricted. Notice that this is written as 4L, wavelength 4L over N. Again, N being odd only, like that. And then lastly, remember that we can write our wave equation frequency as speed over wavelength. Well, speed is going to be this, and then the wavelength we have as 4L over N. And then notice that this is the same as multiplying by the reciprocal, so this times the inverse of this, which then simplifies as NV over 4L. So just writing it nicer, neater. If we want to know what the note sounds like, or the frequency, it's going to be NV over 4L. Like this. N is equal to 1, 3, 5, dot, 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 odd. That's odd, sorry. Odd. Like that. So, some consequences of this, first of all, is that make sure on your equation sheets, you make sure that you note this as closed pipes, because it's different than the open pipes. Excuse me. Open pipes has a factor of 2 and have any integer, and this is for open pipes, like this. Now notice that you have 4 versus 2 right here. So notice that the bigger this number is, the lower this note. So generally, closed pipes will make lower notes. In fact, unfortunately, I don't have this to show you as a demonstration, so I'll just talk about it verbally. If I have a pipe of like L, for example, like this, and I hit it, called the boom whacker, like I said, will make a noise like donk. But if I put a cap on that same pipe, so put like a cap at one end, it will go donk. And I know that I can't really draw that, but this would make a lower note than this. In fact, between these two is called an octave, which it means it's just the same note, but higher or lower. So this would go donk, this would go donk, just like that. It's actually a pretty cool demonstration, so it's too bad I can't really show you in this video. But if you have the ability to do such a thing, it's definitely worth doing it. So that is your that is your closed pipe analysis. These are some of the waves. Let me come back to my slides here. So these are right here talking about the open pipes and closed pipes. So if you notice, this is open and open here for an organ pipe. So you have some organ pipes that are open like this, and notice the antinode and node, so they use an A here. But when you have a closed pipe, like put in a top on this and just having it right here, you can see that you have an antinode and a node for the same reasons. So here you can see where this equation comes from. And then, although this graph has two things going on, I hope you notice that for an open pipe, we're following the blue line. So the motion of the particles is what we're drawing the standing wave. So notice that it's open on both ends with two antinodes. And then notice the blue line here like this with the closed pipe like that. So that's a comparison. So this video, I'm going to go ahead and load it up. shows you how the mouthpiece changes the instrument. Before I let it play, what's happening is the flute acts as an open end and the clarinet acts as a closed end, and what he's doing here is he actually switched the mouthpieces. And even though he's playing a flute mouthpiece, this sounds like a flute. So it's not the instrument that makes it sound different, it's the opening, which just blows my mind, right? Like, I feel like it should play like that. So watch this as he does that.
What are these strange instruments? We could call them superpositions of a flute and a clarinet. Here we use them to demonstrate standing waves in sound. The flute is open at both ends, so the air is free to move in and out, but the pressure is close to atmospheric. The clarinet is open at the bell, but at the mouthpiece, it's almost completely sealed by the reed. So the pressure is large, but there's little air motion. Let's picture the reflection of a pressure pulse.
Okay, so what I'm going to do is just skip this part, although it's definitely worth watching. What I want to show you is just the end result here. Because he does all this math, which is related, but a little different than what I did, so I don't want to confuse you. I do want to show you this, though. Oh, no.
And the cylindrical clarinet.
Okay. This next part, he's going to play the harmonic series of each.
While the clarinet has only the odd members.
Okay. So those are the two main things I wanted you to get from this video. It's definitely worth watching the whole thing, especially if you're interested in music. But notice that the clarinet even sounded lower than the flute. And I think we kind of know that already, but the reason why is because of the mouthpiece. When you go from an open pipe or a closed pipe, it changes the way an instrument sounds. One last thing, and that'll be it for this video. Is this Rubens tube video. So, I don't know if I can click on this, so give me a quick second. Is you can't really see standing waves because they're air and it's hard to imagine. But this will actually show you some standing waves pretty well. I'm not going to show you the whole video, but you can see part of it.
Let's do a classic physics experiment called the Rubens tube. Now, I really want to bring it down, but it involves open flames, and some people have issues with open flames. So, what we have here is a length of PVC pipe. It has about 100 or so holes drilled at half-inch increments. It has a foil tape to keep it from melting. On this side, we've got a 2-inch speaker matching the diameter of this 2-inch tube. On that side, we've got some lab tubing leading to some propane. So let's fire it up and see what it does. Alright, as you can see, we have some nice standing flames, a little bit of oscillation from the vibrations in the hose. Let's throw some sound in there and see what happens. Let's start with a 449 hertz frequency. As you can see, this sets up a standing wave, and we can see, well, the emerging sine curve that represents sound. What happens here is that we're having the sound compressing here and not compressing here. The lower pressure here allows more gas to escape into the atmosphere, shaping the sound curve. Now, if we change the frequency,
Notice that only certain frequencies work.
we set up a standing wave, we get that sine curve. Higher the frequency, the more waves. Now let's throw some music at this. How about some Dave Brubeck?
So remember, amplitude represents the loudness.
Sound visualization with fire.
So the louder it is, the higher the flame.
Terribly energetic, so let's try something a little more energetic.
Okay. So once again, a cool video, worth watching in its entirety, but it shows you how you can make that standing wave. I'm just going to quickly come back to the one that he made over here. There we go. So once again, what you're seeing is with the gas, there's a compression right here. So that means the air can't move, but right here is an antinode, so the air can move. So this is how you can visualize these standing waves in a pipe. One last thing I want to show you, I know I said that before, but closed pipes, harmonics, is because I know my drawings aren't the best, so I just wanted to find a better drawing for you so you can kind of see. This is Pinterest. Don't want Pinterest. Let's see. No, I don't want that one. Okay. Well, anyway, so notice the drawings that I did. This is what they're supposed to look like, and they're nice. Excuse me. They're nicer form, right? So here's the first harmonic. Now, I don't like the fact that they use this because they call this the second harmonic, but technically this is the third, so be careful. I will say third harmonic and mean the third harmonic, not the 1, 2, 3 down. I will say third harmonic is this one, because notice how they use the word fifth right here, so that's really misleading. But the point is, look at these drawings, right? 1, 3, 5, and then they're comparing it, of course, to the open pipe. So you're going to have some multiple choice questions with this, okay, where I'll have a drawing and I'll ask you what's the standing wave number, you know, what's the harmonic number, all that fun stuff, and drawing. All right. So in conclusion, in a summary, standing waves in closed pipes, open on one end and closed on the other, but in closed pipes is you have a node at one end, an antinode another, and because of that it only selects out quarters of the wave, and because of that it also will only go in odd integers. Excuse me. And to solve any of our problems, it's the same criteria except we have a 4L here instead for the factor. N is the harmonic number, V is the speed of sound in the air pipe, L is the length of the pipe, and F is the frequency of the wave. I am so sorry, I'm still sick. I'm going to get a drink of water, but I hope this was helpful.